The information entropy duality paradox is one of the most fascinating puzzles in both physics and information theory. At first glance, information and entropy seem like complete opposites. Information brings clarity, structure, and meaning. Entropy, on the other hand, is associated with chaos, randomness, and loss of usable energy. So how is it possible that these two ideas, order and disorder, are not only connected but actually reflect the same underlying phenomenon? To understand this, let's start with entropy as defined in physics. Entropy, originally introduced in thermodynamics, measures the amount of disorder or randomness in a system. In a closed system, entropy tends to increase over time. This is the second law of thermodynamics, which explains why hot coffee cools down or why a tidy room tends to get messier, not cleaner on its own. More entropy means less usable energy, more uncertainty. Now, contrast that with information. In computer science and communication theory, information is often seen as the opposite of uncertainty. For example, if I tell you something new, I've reduced your uncertainty. That is, I've given you information. In fact, Claude Shannon, the father of information theory, mathematically defined information in terms of uncertainty. The more uncertain or random a message is before receiving it, the more information it can potentially carry when decoded. So here's the twist. Shannon's measure of information uses the same mathematical formula as entropy. It's called Shannon Entropy. The more unpredictable a message is, the more information it contains, just like in thermodynamics, where the more disordered a system is, the higher its entropy. This leads to a profound insight. Information and entropy are not opposites at all. They are two ways of looking at the same fundamental process. Think about flipping a coin. If a coin always lands on heads, there's zero uncertainty and thus zero information in the outcome. If it's a fair coin, you're uncertain whether it will be heads or tails. When the outcome is revealed, your uncertainty is resolved, so you gain one bit of information. But to reach that point of maximal information, the system must have maximum entropy beforehand. The potential for information lies in entropy. How does this relate to the physical world? Take black holes, for example. In modern physics, black holes are said to have maximum entropy, so much so that their entropy is proportional to the surface area of their event horizon, not their volume. According to physicists like Jacob Bekenstein and Stephen Hawking, the more entropy a black hole has, the more information it is hiding inside. This leads to the black hole information paradox. Is that information lost forever when matter falls in? Or can it be recovered somehow? In quantum mechanics, things get even stranger. The famous EPR paradox and quantum entanglement show that information about a quantum system is spread across its entire wave function, not located in a single particle. As systems become entangled, their combined entropy changes, but the total information about the system is preserved. This hints that entropy and information are not just mathematical tools, but may be central to how reality itself is built. What does this mean for us? Every time you learn something new, reading a book, observing a phenomenon, or measuring a particle, you are transforming entropy, randomness, uncertainty, into information, structured knowledge. In this sense, information is entropy viewed through the lens of knowledge. So, is disorder bad and information good, or are they both necessary to describe the same process from different angles? This is the heart of the paradox. Just like light is both a wave and a particle depending on how you observe it, entropy and information are dual aspects of the same thing. The flow and structure of data, energy, and understanding. This duality has far-reaching implications for everything from artificial intelligence and computing to cosmology and consciousness. Could the universe itself be a vast information processing machine, transforming entropy into structure through the laws of physics? And if so, where do we fit into this grand transformation? Entropy is a measure of disorder or randomness in a system originating from thermodynamics. As energy spreads out and systems move toward equilibrium, entropy increases, following the second law of thermodynamics. High entropy corresponds to less usable energy and more microscopic configurations. Entropy thus represents the hidden microstates that a system can occupy without changing its overall macroscopic appearance. Melting ice increases entropy as the ordered structure of ice crystals becomes disordered liquid water. Entropy is like a shuffled deck of cards. Many arrangements look random, but they are all valid states. In information theory, entropy measures the uncertainty or unpredictability of a message source. The more uncertain the outcome, the higher the entropy and the more information it can carry when known. A perfectly predictable message carries zero new information because there's no surprise. Thus, information and entropy are linked. Gaining information reduces uncertainty, entropy, while lack of information increases it. Receiving a secure password lowers entropy by revealing a previously unknown and unpredictable string. It's like turning on a light in a dark room. You reveal what was hidden. Information can be considered negative entropy or neg entropy because it imposes structure and reduces disorder. This idea, proposed by Schrödinger, suggests that living organisms maintain order by importing information and exporting entropy. Paradoxically, to store and process information, physical systems must generate entropy elsewhere due to thermodynamic constraints. Therefore, creating or using information always involves an entropic cost. The brain consumes glucose and generates heat, entropy, to form and retrieve memories. Like a tidy room that stays clean only because someone is constantly cleaning and discarding waste. Maxwell's demon challenges the second law by proposing a being that can sort fast and slow molecules, decreasing entropy. However, modern physics shows that the demon itself must process information, and this information processing incurs entropy. This reinforces the duality. To reduce entropy in one place via knowledge, you must increase it elsewhere. The act of measuring and deciding is entropically costly, preserving thermodynamic laws. A sorting robot that decreases entropy in its task must still expend energy to run its sensors and logic. Like organizing your files on a computer, it takes CPU power and generates heat despite creating digital order. Black holes famously link information and entropy through the Bekenstein-Hawking entropy formula, which says the entropy of a black hole is proportional to its surface area, not its volume. This means black holes store maximal information about the matter they swallow, but how this information is preserved or lost has led to the black hole information paradox. Recent theories like holography and Hawking radiation suggest that entropy and information are fundamentally interchangeable at cosmic scales. As particles fall into a black hole, their properties are thought to be encoded in subtle fluctuations at the event horizon, like shredding a document. Its pieces still hold the information, but it's almost impossible to reconstruct. Any attempt to communicate information by transmitting, storing, or processing requires energy dissipation and thus generates entropy. According to Landauer's principle, erasing a single bit of information has a minimum energy cost, linking physical and informational realms. This highlights the inseparability of information in thermodynamics, making clear that no information system is free from entropy. Every time a digital file is deleted, heat is released from the computer's processor. Like burning a letter after reading it, you've gained knowledge but left physical disorder. In quantum systems, entropy describes how mixed or pure a quantum state is. When two systems are entangled, the information about one affects the entropy of the other. Measurements in quantum mechanics cause a collapse that reduces uncertainty entropy in one part but may increase it elsewhere. Quantum information theory thus connects entropy to probability amplitudes, making the information entropy duality even more fundamental. Measuring one half of an entangled photon pair gives immediate information about the other, reducing uncertainty, like opening one envelope in a matched pair to find both lottery numbers inside. Cells use entropy strategically to drive processes like protein folding, molecular binding, and DNA replication. Biological systems appear ordered, but they actively manage and export entropy to maintain that order. Enzymes, molecular motors, and signaling pathways extract information from noisy environments to support life. This duality of entropy and information enables evolution, adaptability, and intelligence. A protein folds into its functional shape by reducing internal entropy but increasing the entropy of the surrounding solvent. like a book being written in perfect order while the room around the writer becomes a mess. Modern AI systems operate on vast amounts of data, extracting structure from noisy entropic environments. Machine learning algorithms reduce entropy by identifying patterns, but they require computational energy that increases entropy elsewhere. There's a trade-off between model accuracy, information gain, and computational cost, entropy generation. As AI models scale, optimizing this balance becomes critical for sustainable computing. Training a large language model consumes gigawatt hours of electricity, generating vast heat while learning to predict language. Like teaching a super intelligent student who requires a power plant to study each book,